Good day, chem students. Today we're going to have our last lesson of the year, actually, and we're going to talk about intermolecular forces. So we've been referring to these things, intermolecular forces, throughout this unit. We had a little mini lesson on what they were, but we're going to talk about how they actually form, uh, as well as the differences between the different types and what kinds of intermolecular forces different compounds have. All right. So we've mostly been talking about water, but there are other ones as well. Okay, so you should be able to, by the end of this, explain the different types of intermolecular forces possible. So there's dispersion, dipole, hydrogen bonding, although we call it London dispersion, dipole, and then hydrogen bonding for those as well. We're also going to talk about ionic in here. I don't know why it doesn't say in here. But so we should be able to also compare and contrast polar, nonpolar, and ionic bonding in terms of IMFs. There we go. There's the ionic bonding. So what's the differences between these things in terms of the IMFs, those intermolecular forces of those types? Okay. And you should be able to do examples of each type. All right, so the first one, London dispersion force. This is the weakest type of intermolecular force that we have. Um, I'm not sure why it's called London dispersion force, to be honest, but essentially this is between nonpolar covalent molecules. Um, you have to remember that these intermolecular forces between all these particles, all different types, really it's just a positive and a negative charge that is attracting to each other. It's electrostatic. That's what that positive and negative charges mean, or that's a word for meaning positive and negative charges. So having an area of positive and an area of negative on a molecule means that you're going to have IMFs, intermolecular forces. Well, you guys know with nonpolar uh, covalent molecules, they're all covalent, all nonpolars. Um, we know that these nonpolars don't have poles. That's why they're called nonpolar, right? They don't have areas of positive and negative. You've got something like a diatomic right here, this rather annoying animation that just keeps playing. So something like Cl2, like two chlorines together, right? There's no electronegativity difference, so there's no area where you're going to have a pull of electrons to one side or the other. Something like this CH4, we talk about our hydrocarbons, or if it has C and H together, then that's nonpolar. Uh, so this is CH4, and sure enough, right, just because of the organization of it, it's nonpolar. But we can have times where you get poles actually, and those are called London dispersion forces. So atoms of a nonpolar molecule equally share those bonding electrons. Normally, there's no overall charge. That's just summarizing what I just said. Um, this is all diatomics, compounds of C and H. These are nonpolar. Okay, but at any given time, electrons in a molecule are unevenly distributed because those electrons, they're moving all over the place. They're like a cloud of electrons and they're all over the place. So this actually causes temporary dipoles, so temporary charged regions to form, which leads to attraction between molecules. So literally those molecules, those electrons are moving around all the time like crazy, right? And at some given point, all of a sudden, it's not like they stop. This is just kind of like freeze frame. They may be on one side of this molecule, or a majority of them might be, in which case you end up having areas, these dipoles, areas of charge. So you have a negative side of the molecule and a positive side, just because those electrons are moving around randomly. And it happens, they move so fast that it happens all over, a lot, but it's minor. It's a minor amount of charge. Same thing with like two fluorines, diatomic version of fluorine here. So you might have a time where more electrons are over here, and therefore these ones get pulled over as well. Uh, because they're attracted to the positive part here. Uh, and those being on this side means that it's going to push these ones over, these electrons, because they want to get away from the negative charge over here. So you create an area of positive charge and an area of negative charge. And therefore you get some attraction between these molecules. And this is all that London dispersion forces are. So London dispersion forces, it's just these temporary areas of charge from the electrons moving randomly. And at some point they create these dipoles and they're attracted to each other. All right. So, and again, these are happening in non-polar molecules. CH4, another example here. Get two CH4s. At some point, those electrons are going to be over on this side. You end up with a negative side and a positive side. Temporary dipole. It pulls these electrons even over as well, and creates a negative area. And so they are attracted to each other for a temporary amount of time. Now, something to mention, nitrogen, N2, you guys have heard of liquid nitrogen. I'm assuming you know it's very, very cold, right? If you can dip things in liquid nitrogen and they freeze solid. I forget what the temperature of it is, but it's like minus 200 something degrees Celsius. Think about our whole phase change things here, right? To end up getting a liquid with nitrogen, it needs to be super, super, super cold because it has such weak amount of IMFs. To get those IMFs to hold enough to make it into a liquid, because they're London dispersion forces, it needs to be so cold that those molecules are barely moving, those nitrogen molecules. And because they're barely moving, enough IMFs can form to turn it into liquid nitrogen. At any time it goes a little bit higher than that, like minus, I got to find out what the amount is here. Liquid nitrogen, hold on. So I'm just looking on Wikipedia here, hold on. Right, so the boiling point when it turns to a gas is 195 degrees Celsius. That's minus 195 degrees Celsius. So even just having a little bit of energy on those molecules, those N2 molecules, turns it into a gas because their IMFs are so easy to break because the IMFs are super, super weak because they're these London dispersion forces. And yeah, the melting point. So you can get solid nitrogen, but it's minus 209 degrees Celsius to get to a solid. So it has a very narrow range where it's actually a liquid, like 10, 15 degrees, something like that. Okay, the next type. So London dispersion forces, and now we've got dipole-dipole. The reason it's got two of them, two dipoles here, is because they have two dipoles. One here, one here. So one atom of a molecule pulls the shared electrons closer than the other. This unequal sharing due to difference in electronegativity. This is the stuff that we learned about in solutions, the thing about electronegativity. This is about a polar molecule right here. So this causes a permanent negative and positive areas of charge. So in this example below here, we've got chlorine. It is pulling more on those electrons than hydrogen can. Hydrogen's super weak. It's got just a single proton. It does not have much attraction for those electrons. So it ends up just more things get pulled over to the chlorine because of that. This creates those permanent areas. You have a negative side and a positive side. Polar ends attract other polar covalent molecules. So we would get if we had a bunch of hydrochloric acid together here, the chlorine side would be attracted to this hydrogen side over here. So it would create pretty relatively strong, especially compared to London dispersion forces. As we go through these, they're getting stronger and stronger. Okay, so this would be like NaCl or something like that, and this is hydrochloric acid. You have a positive side, negative side. It's permanent dipoles, and therefore the chlorine attracts to the hydrogen side, and the chlorine over here attracts to this hydrogen side. And so those are the intermolecular forces right there. So relatively strong, not our strongest though. Okay, the next one you've probably heard of at some point. It's called hydrogen bonds. And these are special dipole-dipole force. So it's kind of like a special class of dipole-dipole. It's the extra strong version of dipole-dipole, basically. And that is just because it's any substance containing hydrogen bonded directly to oxygen, nitrogen, or fluorine. And if you remember anything about electronegativity, and you can look on your periodic table, these have some of the highest levels of electronegativity on the periodic table. Fluorine is the highest. Oxygen's very, very high, as is nitrogen. Because they have so much pull and hydrogen is such a little weakling, it creates very, very strong dipoles, basically. Those oxygen, nitrogen, fluorine pull extremely hard on the bonding electrons, which creates very unequal sharing and large dipoles. So an example, we've got NH4, which is ammonium, and we've got uh, water, right? In both cases, you've got the thing that isn't hydrogen pulling those electrons away from the hydrogen. And therefore attracting to each other because they have those dipoles. Okay, so these are polar molecules as well. All right, and the fourth and last and strongest one is ionic attraction. Now keep in mind everything else we've been talking about, all these other things, these are molecules in the first place that we're talking about. Whereas once we get to ionic attraction, we're talking about ions. These are ions in the first place. So we've got, this is a classic picture for sodium chloride, right? You've got your sodium here and your chlorine right here. And the sodium has lost an electron to the chlorine. So it already has a negative charge. It has a positive charge. And because IMFs are all about that negative and positive charges just being attracted to each other, this is an ideal situation, right? So those positive and negatively charged ions, they're held together by electrostatic forces. And that's extremely strong. It gives these ionic compounds very, very high melting and boiling points. I forget what it is for salt. It's like 700 and something degrees for its melting point for salt. So very high. So you guys have seen this chart before, and now it's just kind of got this part in it here. So with the bonds, you got, hold on, shared electrons, and if the electrons are lost or gained, then we end up with those ionic bonds, right? And within this, the nonpolar covalent, that's where our London dispersion forces are, right down here. So they're temporary, they are weak. Things that are like diatomics or molecules of carbon hydrogen mixed, CH4, stuff like that, hydrocarbons. And then our polar covalents, these we already knew have a polarity to them. That's either your dipole-dipole or hydrogen bonds. This is permanent instead of temporary. And something like hydrochloric acid or water, those are both pretty strong polar covalents right there. And then lastly, our electrostatic attraction for ionic bonds, which is the permanent and the strongest type of IMFs. Okay, and thinking back here, when it talks about these having really large melting and boiling points, again, that goes back to what we've been talking about. To get enough, you have to get enough energy to break those IMFs, to change phases, to break those intermolecular forces. So that is why our salt or ionics have such a large melting and boiling point, is because they have such strong IMFs that they don't want to phase change. They don't want to get enough. They need tons and tons of energy to break those IMFs. let's talk about water a little bit here. So again, the difference between, just a note here, intramolecular forces and intermolecular forces. Don't get those confused. All right, so let's compare some melting points, various compounds. So we've got our compound, we've got our mass in atomic mass units, and our melting point. Methane, which is CH4, that's London dispersion forces right there. That's what the DISP stands for. And you can see that it has the lowest melting point because, again, weakest forces, weakest IMFs, mean it does not take a lot of energy to actually melt that from a solid. Then we've got our dipole-dipole right here, carbon monoxide. This has also a very low melting point, but it has a bigger atomic mass unit. So keep that in mind that that's why that has it like that. Okay, and then hydrogen bonding. So we've got NH3, and it's got a melting point of 78 degrees, minus 78 degrees with hydrogen bonding. And then water as a hydrogen bonding has a melting point of 0. So why is water so strong? Why has it got such a high melting point compared to these other molecules? Okay. Well, the increase in IMF strength accounts for the increase in melting point. Hydrogen bonding with oxygen is one of the strongest. It's not the absolute strongest. It doesn't, I'm not counting ionic, but I'm pretty sure that hydrogen with fluorine is stronger. I could be wrong. By electronegativity, it should be. Okay. So because that bond is so strong, our melting point is so much higher. We need so much more energy to break those bonds from a solid. If we compare these boiling points of water and similar compounds right here, generally as mass goes up, we should see our temperature going up that we need for boiling points. And I'm just going to bring this over really quickly. This was from an old PowerPoint. This is from heat curves and forces, lesson 4. We talked about generally as mass increases, melting and boiling point also increases. So we had our mass increasing, like propane, butane, octane. Octane has the biggest mass, 114. So then its melting point was the highest. So you would think that it would follow that same, the same pattern here, where water having a lower mass than any of these other compounds should be down here, right? I mean, follow the line of best fit. It's fairly obvious. So why does it have such a high boiling point in comparison? Again, it's the strength of those bonds. So hydrogen bonding holds water molecules together very, very strongly. It's responsible for this higher than expected melting point and boiling point. It's also responsible for the high surface tension of water. So you guys have seen this, a drop of water on something and the way it just beads, stays together. Those intermolecular forces are pulling those outside molecules towards the mill and creates this little dome of water. Okay. So it's also because of hydrogen bonding that ice forms these unique crystal shapes, which are six-sided, having an area greater than liquid water. So this is a liquid, and this would be a solid because of the way they form these crystalline structures here, basically. So ice is less dense than water, which is very different than most solids. And we've talked about this in the past. Most solids are more dense than their respective liquids. So it's a bit of an odd duck. Okay, so now you should hopefully be able to explain the types of intermolecular forces possible. So you should know the difference between London dispersion, how it works, dipole-dipole, hydrogen bonding, as well as the strength between polar, nonpolar, and ionic bonding in terms of IMFs. So how do they all work? How do they compare to each other? And you'll be good. And if you can come up, if you have examples of each one as well. So yeah, that's it for today. Have a great day, guys.